Hello, I am Sapna Davis of EC Department, Rajagiri School of Engineering and Technology. In algebraic structures, we are going to discuss about groups, rings, and fields. Group. A set G on which a binary operation dot is defined is called a group if the following conditions are satisfied. First one, closure property. If A and B are elements of G, then C equal to A dot B is also an element of G. Second one, associativity. If A, B and C are elements of G, then A dot B dot C equal to A dot B dot C. Third one, existence of identity element. For all A in G, there exists an element E in G called identity element such that A dot E equal to E dot A equal to A. Fourth one, existence of inverse. For every A in G, there exists an element A dash in G called the inverse of A such that A dot A dash equal to A dash dot A equal to E. Commutative group is a group which satisfies the four properties along with the commutative property. Commutative property is for all A and B in G, A dot B equal to B dot A. Example, the set of integers with the addition operator is a commutative group. The number of elements in a group is called as the order of the group. A group of finite order is called a finite group. Rings. A ring R is a set of elements with two binary operations, dot and star. The first operation should satisfy all the five properties of a commutative group. Properties of first operation: closure property, associativity, existence of identity element, existence of inverse, and commutativity. Properties of second operation: closure property, associativity, distributivity, which is defined as A star B dot C equal to A star B dot A star C. Commutative ring, ring in which a commutative property is satisfied for the second operation. Example, the set of integers with the addition and the multiplication operators is a commutative ring. Fields. A field is a set of elements with two binary operations denoted by dot and star. It is a commutative ring. Properties of first operation: closure property, associativity, existence of identity element, existence of inverse, and commutativity. Properties of second operation: closure property, associativity, existence of identity element, existence of inverse, commutativity, and distributivity. Galois fields. Finite field has finite number of elements. For a field to be finite, the number of elements should be p raised to n, where p is a prime number and n is a positive integer. Finite field with the p raised to n elements, where p is a prime number and n is a positive integer, is called a Galois field, and it is denoted by g of p raised to n. G of 2 raised to n is commonly used. When n equal to 1, we get a g of 2 raised to n equal to g of 2. The elements of g of 2 are 0 and 1. Addition and multiplication operations are shown for g of 2. Polynomials. In g of 2 raised to n, there are 2 raised to n number of elements. Hence, n bits are required to represent each one. It is easier to work with polynomials of degree n-1 for the n-bit elements. Fx equal to an minus 1 x raised to n minus 1 plus an minus 2 x raised to n minus 2 up to a0 x raised to 0. Coefficients of the terms are either 1 or 0. Example, polynomial representation of a 8-bit word 100110001 is x raised to 7 plus x raised to 4 plus x raised to 3 plus 1. Similarly, 8-bit word for x raised to 5 plus x square plus x is 001001110. Primitive polynomial. A polynomial fx over a field f is called irreducible if and only if fx cannot be expressed as a product of two polynomials of degree lower than that of fx. Primitive polynomials are irreducible polynomials. Irreducible polynomial examples are given in the table. Construction of Galois field. Construct a Galois field g of 2 raised to 3 using the irreducible polynomial fx equal to x raised to 3 plus x plus 1. The elements of gf2 raised to 3 are given as 0, 1, g square up to g raised to 6, a total of 8 elements. To find the elements, f of g equal to 0 can be used. That is, f of g equal to g raised to 3 plus g plus 1 equal to 0. Therefore, g cube equal to g plus 1. Similarly, we can find g raised to 4, g raised to 5 and g raised to 6. The 8 elements of gf2 raised to 3 and its polynomial representation and also the binary representation are given in the table. Another example for construction of a Galois field gf2 raised to 4 using the reducible polynomial fx equal to x raised to 4 plus x plus 1 is given. Error control coding. In error control coding, redundant bits, that is, bits which carry no information, are used to detect and correct errors. Channel encoder and decoder are used for error control coding. Disadvantages are increased bandwidth, system becomes more complex due to channel encoder and decoder. Codes for error detection and correction. Parity check codes. Parity check adds a redundant bit to a bit string. Even parity means a parity bit 1 is added if the data has odd number of ones. Otherwise, bit 0 is added, making the total number of ones in the frame even. Odd parity means a parity bit 1 is added if the data has an even number of ones. Otherwise, bit 0 is added, making the total number of ones in the frame odd. At the receiver, decoding consists of testing the modulo to sum of the received code word, and we should get 0 for even parity and 1 for odd parity. If there are even number of errors, it cannot be detected. Also, it cannot detect which bit is in error. Even the parity bit can be in error. This scheme has 1 bit error detection capability but no error correction capability. Linear block codes. In linear block codes, k-bit messages are encoded into n bits by adding n minus k number of check bits. 2 raised to k number of messages are possible and hence 2 raised to k code bits are generated. N will be greater than k. Linear block codes are also called as NK block code. NK block code is said to be NK linear block code if the modulo 2 addition of any two code words will produce another code word in the NK block code. And it is said to be systematic if k message bits appear either at the beginning or at the end of the code word. Matrix description of a linear block codes. Let the k-bit message be represented as a row matrix U equal to U1, U2 up to UK. The encoder adds n minus k check bits. The code vector is V equal to V1, V2 up to Vn. If the k message bits are placed at the beginning of the block code, then the code word structure V equal to V1 to Vk that will be representing the k message bits. Then Vk plus 1 to Vn will be representing the n minus k check bits as given. The code vector V equal to U multiplied by G, where G is called as the generator matrix of size k by n. The structure of G is Ik slash P, where Ik is the identity matrix of order k and P is the parity matrix of order k by n minus k. If we write G equal to P slash Ik, then the message bits will be placed after the check bits in the code vector V. From the equation, we can see that Ik retains the message bits U1 to UK and P adds the redundant bits. For every generator matrix G, there exists an H matrix with n minus k linearly independent rows such that all rows of G are orthogonal to all rows of H. H is called as the parity check matrix. So V is a code word generated by G if and only if V dot H transpose equal to 0 and the structure of H is P transpose slash IN minus K. The general encoding circuit for a NK linear block code is given. Pij equal to 1 or 0 and it indicates a connection if Pij is 1, else no connection. The message to be encoded is shifted into the message register and also into the channel via the commutator. Once the entire message enters into the register, parity check digits are formed at the output of the modulo 2 adders and shifted into the channel. And the encoding circuit for a particular example is given here. Syndrome and error detection. Let V equal to V1, V2, Vn be a code word transmitted over a noisy channel, and R equal to R1, R2, Rn be the received code word. The error vector E is defined as R equal to V plus E, where E equal to R minus V or R plus V, and this is equal to E1, E2 up to En. Ei equal to 1 if Ri not equal to Vi, and Ei equal to 0 if Ri equal to Vi. The receiver does not know V or E. When R is received, the decoder computes the syndrome S equal to R dot H transpose, which is equal to S1, S2 up to Sn minus K. S equal to 0 if R is a code word and S not equal to 0 if R is not a code word. If E is a non-zero code word, then R equal to V plus E, which is a sum of two code words and will be a code word due to linearity property, and then the error is undetectable. This type of error patterns are called undetectable error patterns. There are 2 raised to k minus 1 non-zero code words and hence 2 raised to k minus 1 such error patterns. When such error pattern occurs, decoder makes an error at the receiver, and syndrome equal to R dot H transpose. So syndrome can be obtained by the matrix multiplication. Syndrome circuit for the NK code is given. The received message is stored in a register. Then the syndrome bit equations are computed using modulo 2 adders. S equal to R dot H transpose and R equal to V plus E. So we get a syndrome equal to E dot H transpose. So we can say syndrome depends only on the error pattern. To recover the original code word, V equal to R plus E. Minimum distance, let alpha equal to alpha 1, alpha 2, alpha n, and beta equal to beta 1, beta 2, beta n be two code words. The harming distance d of alpha beta between alpha and beta is defined as the number of positions in which they differ. It can be obtained using modulo 2 arithmetic also as given. The harming weight w of alpha of a code vector alpha is defined as the number of non-zero elements in the code vector. For example, if alpha equal to 0, 1, 1, 1, 0, 1 and beta equal to 1, 0, 1, 0, 1, 1, then d of alpha beta will be equal to 4. The minimum distance of the linear block code is the smallest harming distance between any pair of code words, and it is the smallest harming weight of the non-zero code vectors. The harming distance is a metric function that satisfies the triangular inequality. Let alpha, beta and delta be three code vectors of a linear block code. Then d of alpha beta plus d of beta delta will be greater than or equal to d of alpha delta. D of alpha beta equal to weight of alpha plus beta. Now d min equal to minimum of d of alpha beta, and this is equal to minimum of weight of alpha plus beta, and this is equal to minimum of weight of V. So W minimum is called the minimum weight of the linear code V. The minimum distance of a code dmin is related to the parity check matrix H. Suppose V is a code vector, then V dot H transpose equal to 0, and this is equal to V1 H1 plus V2 H2 plus up to Vn Hn. Here H1, H2, Hn represent the columns of the H matrix. If V is a code vector of harming weight L, then there exists L columns of H such that the vector sum of these columns is equal to 0. If there are L columns of H matrix whose vector sum is 0, then there exists a code vector of harming weight L. If no D minus 1 or fewer columns of H add to 0, the code has a minimum weight of at least D. The minimum weight of a linear block code C is the smallest number of columns of H that sum to 0. Error detecting and correcting capabilities. The minimum distance daemon determines the error correcting capability of the code. Consider the 3-bit code words plotted at the vertices of a cube as shown in the figure. If the code words used are 0, 0, 0, 1, 0, 1, 1, 1, 0 and 0, 1, 1, then dmin equal to 2. Any single bit error in the received word locates them on the vertices of the cube which are not code words. If the minimum distance of a linear block code is dmin, then any two code words differ in at least dmin places. So no error patterns of dmin minus 1 or fewer errors can change the code word into another code word. If the received vector is not a code word, then error can be detected. An NK block code with minimum distance dmin is capable of detecting all error patterns of a dmin minus 1 or fewer errors. An NK linear code is capable of detecting 2 raised to n minus 2 raised to k error patterns. Out of 2 raised to n minus 1 possible non-zero error patterns, there are 2 raised to k minus 1 error patterns identical to the code words. Hence, 2 raised to k minus 1 undetectable error patterns, that is, a syndrome will be 0 for all these code vectors. If the error pattern is not a code word, then the received vector is not a valid code word and the syndrome will not be 0. Suppose an NK linear block code has to detect and correct all error patterns whose Hamming weight W less than or equal to T, and if it transmits a code vector alpha, then received vector beta will be equal to alpha plus E. The decoder output alpha cap will be equal to alpha if weight of E is less than or equal to T. The decoder picks the code vector nearest to the received vector beta for which the Hamming distance is the smallest. That is, d of alpha beta will be the minimum. The decoder can detect and correct all error patterns of Hamming weight W of E less than or equal to T provided that dmin greater than or equal to 2T plus 1. Let T be a positive integer such that 2T plus 1 less than or equal to dmin less than or equal to 2T plus 2. Suppose delta be any other code vector, Hamming distances among alpha, beta and delta satisfy the triangular inequality. D of alpha beta plus D of beta delta greater than or equal to D of alpha delta. Suppose an error pattern of a T' errors occurs during transmission of alpha, then the received vector beta differs from alpha in T' spaces and hence D of alpha beta equal to T'. Since alpha and delta are code vectors, D of alpha delta will be greater than or equal to dmin greater than or equal to 2T plus 1. Then D of alpha beta equal to T'. D of delta beta will be greater than or equal to 2T plus 1 minus T'. If T' less than or equal to T, then D of delta beta will be greater than T. If an error pattern of a T or fewer errors occurs, the received vector beta is closer to the transmitted code vector alpha than to any other code vector delta of the code and hence correctly decoded. For a binary symmetric channel, this means P of beta on alpha will be greater than P of beta on delta and beta is decoded as alpha and thus the errors are corrected. The code is not capable of correcting error patterns of weight L greater than T. Suppose D of alpha delta equal to dmin and let E1 and E2 be two error patterns such that E1 plus E2 equal to alpha plus delta. E1 and E2 do not have non-zero components in common places. That is, weight of E1 plus weight of E2 equal to weight of alpha plus delta equal to D of alpha delta equal to dmin. Suppose alpha is the transmitted code vector and is corrected by the error pattern E1. Then the received vector is beta equal to alpha plus E1. D of alpha beta equal to weight of alpha plus beta equal to weight of E1. D of delta beta equal to weight of delta plus beta equal to weight of delta plus alpha plus E1 and this is equal to weight of E1 plus E2 plus E1 and this is equal to weight of E2. If E1 contains more than T errors, the weight of E1 will be greater than T and since dmin lies between 2T plus 1 and 2T plus 2, weight of E2 will be less than or equal to T minus 1. D of alpha beta will be greater than D of delta beta. The error pattern with the L greater than T errors results in a received vector closest to an incorrect code vector. The code vectors and the received vectors can be represented as points in an n-dimensional space. Construct two spheres of equal radii T and locate code vectors alpha and delta at the centers. Let these two spheres be mutually exclusive, that is d of alpha delta greater than or equal to 2t plus 1 as shown. If d of alpha beta less than or equal to t, the decoder will pick alpha as the transmitted code vector. If d of alpha delta less than or equal to 2t, the two spheres intersect. Even if d of alpha beta less than or equal to t, beta is close to delta as it is to alpha. The decoder picks delta as the transmitted vector, which is wrong. An NK linear block code can correct all error patterns of weight t or less if and only if d of alpha delta greater than or equal to 2t plus 1 for all alpha and delta. Hence, t will be less than or equal to d min minus 1 by 2. D of alpha delta minimum equal to d min. It is the largest integer not greater than 1 by 2 d min minus 1. T is called as the random error correcting capability of the code, and the code is referred to as a T error correcting code. Standard array and syndrome decoding. Let Vj equal to j equal to 1 to 2 raised to k be the distinct code vectors for an NK linear block code. For any error pattern E, the received vector Rj is Rj equal to E plus Vj. The set of vectors Rj is called the coset of the code. There are 2 raised to n minus k cosets for an NK linear block code. Rj dot H transpose equal to E dot H transpose. Hence each coset has a unique syndrome. Since the received vector R can be any of the 2 raised to n tuples, we can partition the received code vectors into 2 raised to k disjoint sets using the standard array. The steps involved are given. Step 1. Place the 2 raised to k code vectors with the all 0 code vector as the first element. Step 2. E2 is chosen and placed below V1. The second row is formed as E2 plus Vj. Step 3. Choose E3 and complete the third row as in step 2. Step 4. Continue until all the n tuples are utilized, that is up to E2 raised to n minus k. The table is given. Since all the code vectors are distinct, the vectors in any row of the array are also distinct. Every n tuple appears in one and only one row. There are 2 raised to n minus k disjoint rows or cosets in the standard array, and each row or coset consists of 2 raised to k distinct entries. The first n tuple of each coset is called the coset leader. Suppose dj transpose is the jth column of the standard array, then dj equal to vj, e2 plus vj, e3 plus vj up to e2 raised to n minus k plus vj. The 2 raised to k disjoint columns d1 transpose, d2 transpose up to d2 raised to k transpose can be used for decoding the code. If vj is transmitted, the received vector r will be in dj transpose if the error pattern caused by the channel is a coset leader, and r will be decoded correctly as a vj. If Vj is transmitted and the error pattern E cap is not a coset leader, and let E cap equal to Ei plus Vl, then the received vector is R equal to Vj plus E cap, and this is equal to Vj plus Ei plus Vl, and this is equal to Ei plus Vm. Thus the received vector is in Dm transpose, and it will be decoded as Vm, and a decoding error occurs. Correct decoding is possible if and only if the error pattern caused by the channel is a coset leader. Accordingly, the 2 raised to n minus k coset leaders are called correctable error patterns. Every NK linear block code is capable of correcting 2 raised to n minus k error patterns. To minimize the probability of decoding error, the most likely error pattern should be chosen as a coset leaders. For a binary symmetric channel, an error pattern of smallest weight is most probable, and hence error patterns of smallest weight should be chosen as a coset leaders. Then the decoding based on the standard array would be the minimum distance decoding or maximum likelihood decoding. Suppose a received vector r is found in the jth column and nth row of the array, then r will be decoded as vj. D of r vj equal to weight of r plus vj, and this is equal to weight of el plus vj plus vj, and this is equal to weight of el, where vj is the transmitted code vector. Let vs be any other code word other than vj. Then d of r vs equal to weight of r plus vs, and this is equal to weight of el plus vj plus vs, and this is equal to weight of el plus vi, where vi is a code word. Since el and el plus vi are in the same coset, and el being the coset leader has the smallest weight, so weight of el will be less than or equal to weight of el plus vi, and hence d of r vj less than or equal to d of r vs. Thus the received vector is decoded into a closest code vector. Syndrome decoding or table lookup decoding. Each coset is characterized by a unique syndrome, or there is a one-to-one correspondence between a coset leader and a syndrome. These relationships can be used in preparing a decoding table that is made up of 2 raised to n minus k coset leaders and their corresponding syndromes. Step 1 in decoding is compute the syndrome S equal to R dot H transpose. Step 2, locate the coset leader EJ whose syndrome is S. Then EJ is assumed to be the error pattern caused by the channel. Step 3. Decode the receive vector R into the code vector as V equal to R plus EJ. Decoding circuit. The error patterns can be expressed as functions of syndrome. E1 equal to function of S1 to Sn minus k and E2 equal to function of S1 to Sn minus k. This can be done up to En. The received vector is stored in a buffer register. Then from that syndrome is computed. Then from syndrome error pattern is identified. Then error pattern is added to the received vector to obtain the corrected output.